Hello, my name is Kamarion Porter, and this is my number file video. So we all learned how to count, first by adding things together, then by grouping things together, and then adding lots of zeros to the end of numbers, and then finally condensing all those numbers into scientific notation. Not forgetting the significant figures, of course. But then after that, while these built up sort of the basis of our mathematical knowledge, we never really continue with that trend. We split off into more adding variables, functions, trigonometric functions, things that use these concepts but don't really build upon them. So the question I'm here to answer today is, what if we continued on that trend? Where would that lead us? All right, so we all know that 2 times 3 equals 2 plus 2 plus 2. Likewise, 2 to the third is the same as 2 times 2 times 2. And so we see there's a bit of a pattern here. Why not just continue it on by defining another operator called double arrow? In that sense, 2 double arrow 3 equals 2 to the 2 to the 2. And continuing on, we get triple arrow, which gives us 2 double arrow 3, which is 2 double arrow 2, double arrow 2. And we continue on some more to get 2 quadruple arrow 3, which equals 2 triple arrow 2, triple arrow 2. But because writing 4 arrows each time we want to use operations is a little much, this is also the same as 2 to the 4 arrow 3. And we can continue using this notation to say that 2 to the 100 arrow 3 is the same as 2 to the 99 arrow 2 to the 99 arrow 2 without having to write almost 300 zeros. And notice that all of the operations that we've defined here are actually part of an infinite set of operations called hyperoperations that build on each other in the same manner. And we can define them as follows. For the nth hyperoperation, which we will denote as n, a positive integer a and an integer b that is greater than -1 or equal to. We get the following properties. A, 0b will be equal to 1 plus b. And this 0th hyperoperation is actually what we call the successor function. Where the value of a doesn't really factor into how this operates. The next property we have is that a to the 1, 0 equals a, which is the same as a plus 0. Next we have that a, the second hyperoperation, equals 0, which is the same as a times 0. And then for a to the nth operation, 0 is 1, as long as n is greater than 2. And n is also always going to be a natural number, which is any number that is any whole number that is 1 or greater. And for everything else that falls out of these special circumstances, we have that a and b, the same as a to n minus 1 operation, to a, not b, to the n minus 1 operation, to the n minus 1 operation of a, and all of these will be for b sets of a. Now, as we already kind of hinted out by their special properties, the first hyperoperation is the same as addition. The second hyperoperation is the same as multiplication. The third, exponentiation, which is the same as a to the single arrow b. And then we continue on to the ones that we have already touched on quite a bit. In the a double arrow b, which is called tetration. The fifth hyperoperation is called pentation. And there are also ones after that that are named in similar fashion of like hexation and septation, octation, and so on. But in the general, what we see from here is that the nth operation is for any n that's greater than 2. Is the same as a to n minus second arrow b. And now go over some more proper terminology. So the way we really read the nth operation n in this context is that it's the bth n-ation of a. So as an example, if we had 20 pentation with 10, we'd say that this is the 10th pentation of 20. And for really high numbers, we just use the number itself. So this would be the 10th 40ation of 20. Now, and one other thing is that when referring to this, just this n, the nth hyperoperation, it is very common to refer to this as hyper n. Just a nice little shorthand that I'll use. And one other important thing to touch on before we get into our calculations and examples is that hyperoperations are right-word associative, which means that 2 hyper 4 3 is the same as 2 hyper 3 times the result of 2 hyper 3, 2, which is 2 hyper 3, 4, which is 2 to the 4, which is 16. All right. Now, building off of this, we get that 2 hyper 5, 3 is 2 hyper 4, 2 hyper 4, 2, which is 2 hyper 4, 16. And the result of this is 65,536. Quite the jump from 16. And just fair warning, these are only going to get larger as we go on to the hexation with 2 times 3. We get 2 pentation with 2 and pentation 5, which is 2 pentation of our last result, which is again 65,536. And just to visualize this, this is the same as 2 to the 2 to the 2 to the 2. And there's going to be 65,536 copies of 2 in the sequence. And this is already way more than most calculators can handle. So I guess there's a reason they might have branched off. As you can see, hyperoperations generate extremely large numbers very quickly, and most calculators can't handle anything past single-digit frustration. The one thing that hyperoperations allow us to do is encapsulate extremely large numbers, like the infamous Graham's number. This number is so big that it needs to be generated in steps, even with our newfound operators. The first term, G1, is simply 3 hyper 6, 3, already beyond the scope of most calculators. The second term is 3 hyper G1, 3. And this continues until the 64th term is generated, which is Graham's number. An absolutely ludicrous value that would be very, very painful to write without the use of hyperoperations. Wonder if they have inverses. But that's a rabbit hole for another day. Thanks for watching.